Right. So I'm the main author of GHCJS, and I'm giving you an update of what we've done after last year's ICFP and the things that I'm currently working on. Well, the main thing that I'm really excited about is the GHC 7.10.2 release, which fixes a few annoying bugs that made it hard to install GHCJS. But after I upload the whole thing to Hackage, it will take a few more bug fixes and a bit of coding before I actually am confident enough to do that. Then you can really just cabal install GHCJS and then run GHCJS boot, which builds the libraries that libraries like base and GHC prim, InterGMP, all the libraries that the compiler needs to work. But since it's not on Hackage yet, you can still almost as easily with recent cabal, if you have GHC 7.10.2 and cabal install based on cabal 122, which comes with GHC 7.10, then you can do this with your existing tools. You can just install a snapshot from that location, run the GHCJS boot command, and everything should work. Other than some cabal limitations like cabal not being able to install happy and stuff, but that's not my problem. Someone should fix that. So it's actually possible to install, and people have been using it this year to depend on it for non-toy projects and stuff. So what we actually did in the past year is, well, that's pretty long ago. Cabal support got merged in 122. The first releases of 122 had some minor bugs, but those have been fixed over time. The stack tool by FP Complete also has GHCJS support, at least in an experimental way. I haven't used it really yet, but it should be usable with that too. Last year, a GSOC project added memory profiling. We have time profiling now too. The thing that I spent most of the time on in the first half of this year is a massive rewrite of the GHCJS base library called Improved Base, which I've been telling people to use for a while now. I'll come back to that in a second. And probably the most requested feature after easy installation is a REPL. And I made earlier this summer an implementation of GHCJSI, and I'll explain how that works later. It's still experimental, but it shows that it works. And there have been many small bug fixes, some performance improvements of the compiler, and well, since more and more people are using it, more and more people are trying to get things done, and I have more to fix more and more things, which reduces my productivity a bit. But anyway, the improved base library is a big rewrite of the GHCJS base package, which is the package that comes with GHCJS for JavaScript interaction. And the old version was a very rudimentary thing to access JavaScript objects, to export callbacks from Haskell to JavaScript, or from JavaScript to Haskell. It was really just something temporary. And the new version, Improved Base, I think it has grown from 5 to 70 something modules, and it has bindings for pretty much all of the basic JavaScript language. You can access arrays, typed arrays, numbers and objects, since they're all a bit different from the normal Haskell types. The arrays come in ST, pure, and IO variants, depending on how you exactly use them. If you pass pure ones to JavaScript, you're not expected to mutate them and stuff, but well, that's kind of the expected thing. We also have bindings for many of the standard web APIs, like Canvas used to be in a separate GHCJS Canvas package. It's now been pulled into the GHCJS base library, and many of the other things too. And they've all been wrapped in a sort of Haskell-y way. So your XML HTTP request will do a look from Haskell like a blocking call to the server. None of the async callbacks have to be done manually, so you can use the standard things like system timeout to set time limits on your XML HTTP request, and everything will be handled correctly, like closing connections or even getting partial lazy results will be handled automatically under the hood by the library. And another secondary reason for this rewrite was to set a good example for how to write good JavaScript bindings for other libraries. So expanding this a bit, this should be a good place to look at for current modern best practices for this. And It's not quite complete. The JSON library is not quite done yet. I'd prefer to somehow integrate this with ASIN and have it work directly on JavaScript objects without an intermediate representation, but that might require some API changes. So GHCJS will be released without a full JSON library at first, but eventually this should be added to GHCJS base 2. It's almost ready, and the version of GHCJS that I pointed to in the snapshot installation is also the improved base branch. I think everyone should try to use this version now. It will soon replace the current master branch. So let's get to the next item, the big thing. Last year's GSOC project, one of the GSOC projects, added memory profiling to GHCJS. Just like with DHC, it's based on cost center stacks. So the heap profiling keeps track of how many cost centers have been allocated for, how many objects have been allocated for each cost center stack and how much memory is used by all of them. And it works on the same way as with DHC. You have to install a separate profiling version of each package. So in that respect, it's very similar. Earlier this year, I added the time profiling to the GHCJS. Unfortunately, it's not something that's supported on all platforms, but at the moment it's only supported on Node.js. And the reason is that it uses the built-in statistical sampling profiler from the V8 engine, which takes a sample of the current instruction pointer and call stack to every millisecond records that in a log, and it has a log analyzer to get your profiling report. The GHCJS time profiling is built on that. The only challenge was to make sure that the cost center is recorded somehow in these samples, and that's done in GHCJS by a small npm module that uses some native code to inject these things, and the log analyzer has been modified to make use of the extra information of the cost center stacks. So that's why it's platform dependent. Other JavaScript implementations that do have a statistical sampler, like the Chrome browser, could use the same approach, but they make it really, really hard to install plugins that add native code to the browser. I think they want to avoid another Flash or something happening. So this is much harder on things like browsers, but it's something that should be added over time. And it's really useful since, the somewhat simplified profiling report that you get has all the JavaScript functions. You can see all the lazy compile things are the things compiled by the V8 JavaScript engine to native code. And the cost center things are the Haskell things. They point to a Haskell source file. For example, you see here a cost center P, which with inside the cost center A, and you can even see how much time is spent in a particular JavaScript call stack inside a cost center call stack, just because we completely built on the existing infrastructure of this. So I think this is actually pretty cool, since I don't think GHC even gives you this. But this is just because I could steal this from V8, of course. But it's really useful. But unfortunately, if you have performance problems and you can't run your code, if it depends on the DOM or whatever is only available in browsers, then it might be a bit harder to do. But it's a good start, I think. And the other thing, the most requested feature after easy installation is the REPL. It's experimental, it's easy to break. I just pulled out a copy of the whole GHCI code. I ripped out some parts, and it's a horrible mess, but it works, which is the most important thing, I guess. When you start it, it looks just like GHCI. The only difference is that you get the JavaScript FFI, and well, if you have a browser, then you get access to the document in the browser. So if you just from the command line run GHCJSI or GHCJS-interactive, you get a REPL session just like GHCI, and this thing opens a port which uses a socket.io thing, which is based on WebSockets and some other stuff, which I'm just using for free. And if you connect to your local GHCJSI session, it will it allows the browser to take over the session. So if you enter an expression and after you've connected the browser, it will send the code from the compiled code from the expression to the browser. It runs it in the browser, which means you get access to the whole JavaScript environment in the browser, including the document, which makes it really easy to experiment with this with Haskell with the graphical user interface and all the good things you get from the HTML things and the bad things too. There's one limitation, since it's based on the existing compiler infrastructure. It uses the normal compiled code path. There's no bytecode interpreter, which means that tracing and stepping through expressions is not yet supported. I don't know if many people use it, but I haven't really gotten many requests for this so far. So it's possible to add it, but I. Right. And if someone wants to port it to GHCJS, then well, send me a pull request. Right. Well, so I didn't. Well, this is an example of the session. The left side is just a terminal window. I think it uses Cabal REPL, since that's also supported. Cabal integration is quite complete at the time. It's probably hard to read, but it's just some expressions that the user entered in the terminal, and everything basically works. You can use the JavaScript FFI, and here the user has sent the browser some instructions to add some text to the document. Well, you can probably imagine much more interesting ways to use it, but well, that's basically the main big things that have been added over the past year. Since it's easier to install, more and more people have been using it for actual real non-toy projects, so there are some pretty cool other things coming up too, mostly in terms of libraries like Reflex, FRP, and then there are some DOM libraries, and then so it's cool that it's being used, but the problem still is that the bigger the project gets, the bigger the code gets too, there are more demands on the performance of the compiler and things. And I'm not quite happy where I am yet. So last year I started to try to work on some improvements to fix this stuff. But first let's look at, well, this is the reason why I am not quite as far as I hoped. Last week I was on the West Coast Trail for a week and I forgot my laptop there. So I'm sort of a week behind, a bit more actually, but this is the only excuse that I have. So the short-term goals are to improve the optimizer, to use the latest JavaScript features. The latest JavaScript standard, ES 2015, has been finalized earlier this year. It has tail calls, finally, yay, and they can mean a massive improvement in performance and in just the cleanliness of the code that we can use. So we really want to be able to use them, but we can't assume for at least another few years that it's supported everywhere. So we can't just switch over GHCJS to this and say, well, upgrade your browser. That's not really how it's going to work. That's why we're stuck with JavaScript in the first place. And we also want to make it easier to develop, both for end users and for the compiler. For example, source maps, much of the infrastructure has been merged in GHC 7.10 for keeping track of source location. It's completely complete, and I'm really happy with that, since this allows me to generate source maps. All these things require quite a bit of infrastructure rewrites since the current version of GHCJS isn't quite ready for this yet. Also the compiler is pretty slow. Well, sometimes people complain about code size. Usually when they run the code, they find out it's fast enough, and then they stop complaining for a while until their project becomes really too big. When I look through the code, I often see things like, I can add an optimization rule and just make these things smaller. And 2 years ago, I could just add those optimization rules. But these days, I have mostly the whole GHC test suite imported, so it will probably catch some bug, and otherwise some user will complain after a while, since the current optimizer is really fragile. And the other thing is, if I make a mistake, it's often quite hard to find where it is. So I think over the past year, code size has decreased a bit, since I had to, code size has actually become worse, since I had to disable optimization rules since they weren't quite sound. Also, there's no flexibility in naming, so you get all these very long variable names that you can rename with Clojure compiler, which is a bit horrible since it breaks many libraries. We have no flexibility in supporting module systems. Well, we also have one single target, which is also a problem, since ES 2015 has these very attractive tail calls, but we can't assume that they're there. And we also have GHCJS supports lightweight threads. But sometimes if you, lightweight threads do add a bit of code size, and they have some cost in performance. And there's no way to say, well, I can do without lightweight threads, or give me something a bit simpler. So we want to make the whole thing a bit more flexible, to have more options at compile time. But we can't make it too slow. So we want these options to be a link time option, like link my program for ES 2015 target, or link my program for an older browser. But if linking becomes too slow, then it's just unacceptable. So what we want to do is change the internal representation to allow these things, but without things becoming too slow. So first, let's to see how it's done, or to see what we need. Let's look into how Haskell is evaluated. Most Haskell things in GHCJS in the runtime look like a JavaScript object with a function, some metadata, and some data D1 and D2. The function is the main thing. If it's your object is a thunk, you call that function, you pass it the object itself. Well, I started a bit late. I have a timer myself. Right, if it's a thunk, then you call the function, it returns the result in weak at normal form. If it's a function, you pass it the object and some extra parameters, and it applies the function. This is not quite the whole story, since some things, there's an optimization for some. You don't need to wrap int data or bool or other things that JavaScript can distinguish from objects by language feature, the type of operator in these objects all the time. So the runtime has a shortcut for this, which helps performance. But it's mostly running your Haskell program is calling these functions, starting from the main action until your program is done. Well, if you add threading, that adds a bit of a complication. The thing is, we we want to be able to switch to other threads when we need to. So we can't keep computing in a single thread, keep calling on the JavaScript call stack deeper and deeper. So what we do instead in GHCJS is have a single main loop, the entry point of every computation. The main loop on a conceptual level basically looks like this. It gets threads from the scheduler, at least if there are work to do, and all computations, these function calls, return the next function call to the main loop. The thing is, we don't know anything about these function calls. So when we have the next function to call, we just call it without any parameters, and we have an out-of-band mechanism with global variables to pass all the arguments, which is a bit annoying, but it's the fastest thing I could find, and it works. So if we compile our Haskell program, very simple. If we have f of x and p, where x is maybe a and p is a predicate of a to bool, and we return a bool, then if we have a simple non-threaded function, we first have to reduce the thunk x to a reduced x. Then we check if x is the first constructor. If it's the first constructor, then we return false. And otherwise, we have to apply the predicate to this. If we add threading, we can't call into reducing the thing, so we have to split up the function. We get, just like GHC, our own lightweight stacks. So we get a bit of maintenance things, stack management in our code. We split up the function into two parts. We first reduce the thing, we return the computation, and the rule is, just like in GHC, that when we're done with the computation and we have something in weak at normal form, we return to a continuation that's on the top of the stack. So here, if our constructor is nothing, then we have some global out-of-band argument passing, and we return to and we call the continuation. If we now want to use the tail calls by ES 2015 tail calls, then we really want to get out of this out-of-band passing of things, since well, the JavaScript engines are much better at inlining normal function calls there. So we have to change things a bit, but the changes are far smaller than the change between non-threaded and threaded code. On the right, you can see that our functions get our regular arguments again. It's a slightly simplified picture, since we still do have to return to the main loop sometimes to get our the scheduler to switch to other threads. But it's a fairly minor change. So we have some local changes that we make, but the local changes are made all over the place. So these are the basic main two things that the code generator, the new version of the code generator, has to support. And that's what I've been working on a third version code generator, which replaces the current JMacro by Gershom there based AST with something a bit more GHCJS specific. It's still JavaScript, but instead of working with a completely undecorated JavaScript AST, it's something that basically captures the control flow structures of JavaScript, but adds lots of annotations. All terms have types, which are used by the optimizer to rewrite things. And we have lots of special primitive things like these tail calls for Haskell constructs. And this allows us to rewrite the optimizer and apply rules based on all the types, which makes it much easier to get the optimization rules correct, since guessing things from dynamic types is horrible, at least at compile time. And the other thing is that the code generator is split from one phase into two phases, just like GHC 7.4 I think did, where the first version of the imperative code is non-threaded, just does direct calls on the JavaScript stack, and the second step is the CPS transform code that supports full preemptive multi-threading. Well, with these types and these two versions of the code, since the difference between the non-threaded and the threaded code is fairly big, I found it to be very hard to represent that in some parameterized AST thing as a single thing. So these two variants get recorded separately in the object files. All the symbols have some Haskell origin location. The whole compiler knows where some symbol is from, so you can choose a naming convention at link time, which makes it easy to plug in the future of, say, module systems or global variable renaming of things. And this is a project that's been ongoing since last year, December. It's not quite finished yet, but it should be in GHCJS before the end of the year. I hope you will get it ready before then, but the first version of GHCJS will be released on Hackage without this, and the improvement should be fairly clear, but the main thing is that it makes the whole thing more flexible, and that it allows me as a compiler writer to insert assertions and core linting of the AST, or well, not really core, but this tier linting, to check if my optimizer does things wrong, so I catch them before users catch them, which is usually a good thing. So where are we at? The integration with build tools, Cabal, Stack these days works. If you find any problem, report them on the Cabal tracker. But if you have the latest Cabal, you just should be able to Cabal install --GHCJS some package. Sandboxes work. Oh wait, sandboxes have some small issues. Those are still also caused by not me. The REPL is experimental. You can break it. It's in a separate branch, but it works. The code needs cleanup, so if anyone wants to volunteer, then I'd be really happy to guide them. But the bigger improvements, they really need this infrastructure change that will happen over the coming months that I'm working at the time on. So the first release of GHCJS should be ready in a few weeks. On Hackage, install snapshots, report bugs before then, use GHC 7.10.2, and everything should work out fine. The improved base branch requires GHCJS 7.10. The master branch, which will soon be deprecated, will still support GHC 7.8, but if anyone really needs GHC 7.8 support for GHCJS, speak up, otherwise I'm going to drop it fairly soon. While there are still more things to do, I really like to be able to run automated tests for many more packages than just GHCJS based, like byte string text and many other Cabal packages, just like Stackage I think does for new GHC releases, just to get some more confidence in GHCJS releases. So if anyone is interested in that task, I'd be happy to help out. So that's basically where we're at for GHCJS. Any questions? Well, it's me mainly on the compiler still, but I get more and more help for libraries. And Hamish has been doing a massive maintain. The couch, oh yes, the couch in New Zealand has been really helpful, but he's been generating bindings for the DOM library for document manipulation from the IDL API description, and it generates a massive amount of Haskell code with complete bindings that work on both GHC and GHCJS, by the way. So if you compile things with GHC, you can link them against some say embedded Chrome or WebKit thing. You get a native application. If you get them in GHCJS, you get a web application that you can just run from any browser, which is really cool, I think.